All right. Uh, Welcome back. Today is the 11th of October. We are still in week 8, and we'll be doing the second and third lecture for this week in these 2 hours. Basically, we should be able to finish all these 6.2.2 up to 6.3.3. I would actually go through an overview of these, the details you should be watching from the YouTube directly, but I would present the same thing in a different speed and in a different view so that you guys can appreciate it differently. Okay, with that, then let's begin. So today's focus, I have 4 focus. The first focus is this: the projection of a vector A onto another vector B. Okay, and what is this? And I'm going to draw a geometric picture first for you. And this is the vector B, and this is the vector A. And where is projection of A onto B? So you think of it as here. This vector at this point is called P, is the projection of A onto V. And why are we doing that? Well, there are many reasons. One is we want to find the best one, the best approximate of A in the direction of B. And when we say that, what are we saying is that, well, this is the direction of B. Let's draw a green, maybe I'll find a highlighter. Yep. So this is the direction of B. And I can move it here, 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 anywhere along this line or back even. And I can, I'm allowed to choose any point along this direction of B. Why do I choose this point? And in the Euclidean space, you can see that this is a triangle, and the nearest point along the direction of B is here, is this point. Because let's do a different color now. Because if I choose another point here, for example, then this point has a longer distance to A than this red line, for sure, because then this will form a triangle. So the natural idea is that we want, what do we want? We want the error to be 1. So the best way is the error is orthogonal to what? Can someone type something? Yes, the error is going to be orthogonal to B. Yes, because you see, there is the error vector here, and the B vector is orthogonal, forming a right angle triangle. So with that, actually, then we can think of the idea, the clever idea, right? What's the clever idea? Well, so we start with the first idea that the error must, and the B vector must be what? Guys, when they are orthogonal, the dot product, so this is the dot product, must be 0. Very good. So we start with this. And what is E, guys? So E is, so if we have B here, and this is P, this point is P, so it's P plus E equals to A, right? So we have P plus E equals to A. Therefore, E is equals to A minus P. Right. But what is P? Remember, we told you that P is along P is along B. So we call him alpha, a scalar, times what? P. That's all. All right, so we have all these notations sitting around. Let's collect them. So A minus P dot B is equals to 0. This guy becomes A minus alpha B dot B equals to 0. And now we can open up the bracket. A, the vector A, dot B minus alpha B dot B equals to 0. Therefore, the only unknown is alpha is equals to A dot B divided by B dot B. Can you all see, guys? Okay. So from first principle, we derive how we can find the scalar alpha such that we multiply some vector B to reach this point. So here, then we say, therefore P, which is the projection of A onto B, is some alpha times B, which is A dot B divided by B dot B. This is the alpha, and alpha is the scalar times B. So that's where we get this equation. Okay? And we now know how to project A onto a line B. Now I'm going to write the many equations for you now. Okay? The next equation. So let's start with this equation here. So P is equals to the projection of A onto B. I repeat the equation. A dot B, B dot B. Just remember this little bracket here is a scalar, and B. Now I can write it in a few ways so that when you see different ways, don't get confused. The first way I will change is A dot B is the same as B dot A, right? Oh, okay. So this is one way. So we're not confused. And then what about this guy in the bottom? Remember B dot B is equals to, what is B dot B in terms of norm? Square. Remember the norm of B is equals to B dot B square root. Yes? Yes, very good. So now I can write the third way. I don't want to waste space for us. Oops. Okay. Thank you for participation. Now we write B square, right? And now, of course, B square is of nothing but B, B. So again, we're not happy. So we write B dot A, B, B. Still a scalar. And we are still not happy because we can now distribute the B and the B together. Then this thing is dot A and the other B. And now, what is this? What's this green guy? What's this green guy? He has a special name. Okay, his name is unit vector. Yes, the unit vector along B. And then normally we use the notation, a caret. All right, not the normal. Benedict is the normal vector because the word normal sometimes it means orthogonal. So then we have B dot A, which is a scalar, times. So the notation becomes simpler and simpler, right? Nice. See? So you get to understand from this view. Okay. Let's have a concrete example, shall we? So the concrete example is this. Um, I'm going to draw a vector now. And the vector is 1, 2, 1, 2, 3, 4. And the vector would be, and this guy is P, 4, 0. And the other vector is 2, 3. This is A, 2, 3. So I want to show you the projection of A onto B versus projection of A onto B hat. What is B hat? Someone tell me what is B hat, guys, please. The unit vector in the direction of B. Yes, so this vector here is B hat because it is 4, 0 divided by norm of B, which is therefore become 1, 0. So now the question to you is in a quiz, are they the same or different? Guys, quiz question number 1, A. Very good. So where would it reach? So the second question in the quiz is, where is P? Projection of A onto B. Yes, the answer is the same. Very good. So now the second question is, where is P? Projection of where? Where in this picture? Answer is, come guys, we're going to project A. 2, 0. Very good. So it will reach, so I'm going to write here in green. So this point here is P. It is 2, 0. Okay? And you can work it out. And let's just try so that we and let's just try. So P is equals to A dot B divided by B dot B, B. And we are going to try A dot B, which is A transpose B, B transpose B, B. And then A transpose B is 2, 5 with who? 2, 5 with 4, 0 divided by B transpose B is 16. And then we are multiplying everything by 4, 0. Okay, let's see. And the answer is 2 times 4 is 8. 8 divided by 16 is half. And we have 4, 0. And the answer is therefore 2, 0. Voila, at least we got the first one right. Now let's try the second one. P equals to A dot B hat, right? Now we are not interested in B hat dot B hat anymore because this guy goes to 1. And now we are multiplying by B hat. So A dot B hat is, what is A again? 2, 3, 2, 3. The transpose. B hat is 1, 0 divided by 1. B 1, 0. And the answer is 2 times 2, 3 times 1, 0 is 2. Answer is 2, 0. And the answer is the same. Okay, everybody happy? So in this nice one picture, we answer 2 types of very simple quiz question. More importantly, you can see that I write projection of A onto B in so many different ways, okay? And you have to be very careful. You have to understand that all this gives you the same result. Maybe this is the take-home message today, or at least this slide. All right, so we spent about 15 minutes on this. Oh, I can hear you guys. Can someone say hello, please?
Hola.
Thank you. Okay, so you are still. I'm not talking to a. I remember in the NUS there was this video going around that that guy talked for almost 1.5 to 2 hours, and everybody's telling him that they can't see his screen or they can't listen to him. Okay, so you guys are okay, right? Yes? Okay. Anytime you have a problem, please shout. All right. So let's go from this picture. So let's see this picture again. And our friend, this picture is the projection of a single vector onto another single vector. So now let's see another nice picture. Okay. We want to project y onto W. Then you say it's the same thing, but no more. So I'll give you a simple concrete example. Y is R3, W is the span of, guess, guys, what do you think I'm going to write? The span of what? So as I'm drawing, please think and then see what do you think I'm going to write. Y is maybe, I don't know, this is projection of Y onto W. So what do you think W is, guys, if Y is R3? So I repeat, Y is in R3. Looks like R3, right? Because now I have the X, and the Y. Orthogonal vectors. Yeah, okay, okay. Let's try, huh? Yes, yeah, I'm gonna write orthogonal vectors because life is simpler in orthogonal vectors. But what kind of vectors do you think I will write here? What do you think U1 and U2 I'm gonna write? This be U1 and this be U2. Yes, very good. So 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 you realize that I'm gonna say that U1 and U2 are the standard basis, one pointing along the x direction, the one pointing along the y direction, and in the z direction, we're here. And R3 is sitting on this. So if this is, let's see if I got an example. Yeah, okay. Example again is 1, 2, 3. So therefore, if this is 1, 2, 3, one of, oops, zeros, oops. Right, the first basis is U1, which is 1, 0, 0, 0, 1, 0. So the key idea is this. W in English says I'm spanning by these two vectors. In English will be the what? The the floor, right? The subspace. The subspace, very good. The subspace of R3. Where? Which subspace? The, come on, another word for the subspace. Exactly, the plane. Okay, the XY plane is what I was looking for. The XY plane. Because see, if this is the X plane, and sorry, this is the X line, and this is the Y line, then it's this span, I can cover this whole floor. So W is the vector space or the subspace or the floor. or the xy plane of R3. And what in English? Projection of y onto W. In English, what are we after? Is what? So now the projection of y onto W is a what, guys? Is a line? Is a vector? Is a something? Is a what? Is a normal? No. It's a vector. Very good. Vector of what? Vector. Just now in the previous example was a vector along the direction of B. Now it is a vector what, guys? Yes, vector in W. Very good. So I have to find a vector within the space of W. So that's why it's called vector space. Yeah? Means I'm living in W. Okay? And it's a vector in W. That is what? Some more. I'm going to do projection. So the best approximate, yes, very good, is that is closest to Y. So what does closest to Y means, guys? Is the best approximate. So what does best approximate means, guys? Best approximate of Y on W. What does best means? The error is the smallest. And where is the E, guys? Where is the E? Which color? I have the blue, I have the dash blue, I have the green. Where's the E? And of course, you will tell me that the error is the dash blue error. So now let's try. So this green plus E is Y, right? So I'm going to say this is the projection of Y. We call it Y hat, guys. Y hat, right? The approximate of Y. The notation we use in math is the hat is always the approximate. So if this is Y, this guy is Y hat. So therefore, Y hat plus who, guys? Plus E equals to Y. So it's Y hat plus E equals to Y. And therefore, E is equals to Y minus Y hat. The error. Oh, okay. All right. Now, let's zoom in here. If this is Y, and then what do you realize about this point here? I'm going to show you that this guy is going to be orthogonal. The error is going to be orthogonal to anybody, any vectors on W. Can you all see that? Or let me draw another picture for you. How would the picture look like? The green thing is the plane. Now, can you see that the blue guy, here Y, and here's Y hat 1, and this is Y2. Y2 hat, Y2 hat versus Y1 hat, who is nearer to Y? Well, if Y1 is directly below perpendicular, therefore then there is, and then you can see that there is a triangle here, and the distance along Y to Y2 is the hypotenuse. Y1 to Y is the one of the sides, and the shorter side. The way we want to do is to get the shorter side, so we must be perpendicular. So if you move Y2 closer and closer to this point, then the hypotenuse becomes smaller and smaller until it becomes one side. So this is the argument in the textbook. Right, let me show you where it is in the textbook. So in this page, you will see that y forms one side of the triangle, the smaller side, to y hat. Any other point onto the W space will result in a right angle triangle, and the distance to this point is a hypotenuse, therefore it is longer than this side. Okay, so if you have a problem, look at 6.2.5 in this figure and the explanation here. Theorem 9. Oops. Okay, so now we are back. So the question now is, we know how to, so one, we know how to project y onto a line called B. But now, how to do project of y onto a space. This is a line, single line. This is now a, a vector space. Okay, so I'm going to tell you the answer first, and then maybe if we have a chance, we will derive it. Y hat. Y hat is equals to the, oops, W is a vector space with, I'm going to say, basis, orthogonal, huh? Orthogonal basis first, okay? U1, U2, UN. Now, guys, whenever I give you a vector space, I must give you a basis. And in fact, you can orthogonize any basis. You can choose a set of orthogonal basis. You can choose any basis. What is the basis again? Can someone tell me the definition of a basis, please? Yes, it's vectors that are linearly independent and so it's a set. Okay, first it's a set of vectors. Yes, that are linearly independent, and there must be another condition, and spans, yes, and spans the, a subspace, a space, huh? Whatever space we want, a vector space, a space. So here, in our previous example, our nice example here, I choose this guy and this guy to span W. Can I choose another? Come, give me another. So maybe the quiz question is now I give you 1, 1, 0 minus 1, 0, 0. Is that a basis for W? The same W? Yes or no? So now I give you an example, right? Let's try B1 equals to 1, 1, 0. B2 equals to minus 1, 2, 0. Can I use V1 and V2 to span W? Yes? No? Quiz question, guys? Yes. Very good. Because are these independent? Yes, they are independent. Does linear combination of these two vectors spans W? Of course. Because they are not dependent, therefore it can go around here, go anywhere here. What's not nice about this? They are not orthogonal. How to find orthogonality, guys? V1 dot V2. Once it's not 0, then we know they are not orthogonal. Here, U1 dot U2, very nice. They are orthogonal. Okay. Now, Now, once you have a basis, let's say you have a basis, right? Guys, what do you think I'll write y hat? Y hat equals to what, guys? I have a basis. What do you think y hat looks like with respect to this basis? Can someone type, please? Y hat is this point within W. It's spanned by these two bases. What do you think I will write on the right-hand side? Linear combinations of the bases. Very good. So it'll be alpha times U1 plus beta times U2. So I can write it this way. Linear combinations of the bases, right? I can also write it this way. U1, U2, and then what do you think I'll write here, guys? What do you think I'll write here in this space? In these two elements here, please? Alpha and beta. See? Alpha here, beta here. Right. Very nice. Okay, so we understand now that once we are given a basis, this vector that we are trying to represent are linear combinations of these bases. So we are now in where? Okay, so we are now here. So therefore, oops. So we have, let's not call them alpha and beta. What should we call them, guys? I know. So let's call them y1, y2, up to yn. So y hat is an element of Rn. Then we have y1, y2, yn. Okay, and now y hat is equals to, so just now I show you, right? So actually I'm going to write this way. U1, U2, Un. This guy is y1, y2, yn. And therefore now this is actually y1 the scalar times u1 the vector plus y2 the scalar, u2 the vector plus yn, un. Finish. So the y hat is being approximated by this basis. And now we see this again. Okay. Now, because u1 and u2s are orthogonal, right? Remember, ui dot uj equals to what? So we have now choose to be orthogonal. Therefore, ui dot uj equals to what? What do you think I'll write here, guys? 0. If what? ui dot uj is 0 if I is not equals to j. So that means u1 is orthogonal to u2. u1 is orthogonal to u3. u1 is orthogonal to u4, and so on. But equals to what? Equals to what? If I equals to j. I say orthogonal only, I didn't say octonormal. So here, ui dot ui is equals to the norm of ui square. Very good. Now, of course, we hate this number, right? We hope this number becomes 1. So if it is orthogonal, it is not good enough. We like something called, what's the word? Next word that we like? We don't like orthogonal. We like what? Octonormal. Very good. And when octonormal means this guy becomes 1. So there's a difference between orthogonal basis and octonormal basis. So in this example that I have given you here, is it an orthogonal basis or is it an octonormal basis, guys? Octonormal. Very good. So we have octonormal basis. All right. So now let's play. So now we want to play this equation here. Y hat. And let's start from this y hat. And now we assume that the basis u are octonormal. What is the unknown, guys? In this equation, u's are given, right? Y hat is okay. Let's assume that y hat is given. Then the only unknown is the y1, y2, yn. Okay, so let's try. Y hat, if I'm going to dot product with u1, what will happen, guys? Then the whole thing here, this whole thing, is dotting with u1, right? I should use a different color. That's all. If I dot with u1 on the right hand side, I dot with u1. Now I open up this bracket. So this whole bracket belongs to y hat. y1, u1, dot u1. y2, u2, dot u1. yn, un, dot u1. Then what will happen, guys? So remember this property. If the u's are not the same index, they are orthogonal, therefore their dot product is 0, and you will realize that all this goes to 0. The only thing left is u1 dot u1. And u1 dot u1 is 1. So to get y1, all we need to do is this vector dot with u1. So simple, right? And the reason is because they are orthogonal basis. To get rid of them, and the 1 here is because they are octonormal basis. So now we know how to get y1. So what is y1 again? Let's refresh ourselves. This is y hat. This is y1. This is y2. This is yn. So we are only getting the first element of the vector y hat. So what about the second element? Y dot u2 equals to, guys? So you play with the same game again, and you will get the second element. Y hat dot un yn. Very good. Now, okay. Are we almost done? Okay, so let's come back to this question here. So how to get? So I'm going to try to repeat this. Oh, okay. I'm going to try to copy this. Okay. And then we are going to do the concrete example. 1, 2, 3, right? Okay. y equals to 1, 2, 3, and the basis u1 equals to 1, 0, 0. The second basis is u2 equals to 0, 1, 0. Therefore, the projection y hat, projection of y onto w, and then remember what we say, we want to get y dot, can you complete for me, guys? Okay, I'll write down u1 dot u1 plus y dot u2 dot u2. Now this is for orthogonal basis. If octonormal, it simplifies to y dot u1 plus y dot u2. Which one are we going to use in this example, guys? A or B? A is on top, B is below. B. Because the basis is not only orthogonal, they are octonormal. Because the u1 dot u1 is 1, u2 dot u2 is 1. So let's try. So y dot u1 is nothing but, so whenever I see y dot u1, in fact, I write y transpose u1, scalar u1, plus y transpose u2, scalar u2. Of course, you can write u1 transpose y, there's no problem. So 1, 2, 3, u1 is 1 times 1, 0, 0, plus this guy is 0, oops, y transpose u2 is 2. 0, 1, 0. So answer is 1, 2, 0. So again, the answer is correct. It is on the floor, and the coordinate is sitting exactly 1, 2, 0. This is equals to y hat equals to projection of y onto the space W. Okay, clear, guys? So in the last 45 minutes, 40 minutes, we have done all these, the first two things. All right, let's have something abstract now. What is E, guys? So you know that E is equals to, E belongs to who? Y belongs to R3. Y belongs to R3. Y hat also element of R3, but a subspace. What does E belongs to? R3. Yes, it still belongs to R3, but not in this W space. It belongs to who? It doesn't belong to the W space. Y hat belongs to the W subspace. Can Y hat belongs is an element of R3, but it's in an element of W as well. Y is an element of R3, the complete R3. E is also an element of R3, but it is not in the element, not an element of W. It is an element of, guys, what's the answer? Complement, very good. W per, excellent. So if this is the space of W, where is W per? How to find? So W per is a what? A vector space also. Spanned by, so quiz question number 4, I guess. W pub is spanned by who? Can you give me the easiest? Very good. 001. Right, 001. So you see, this is U is 100 here. The other guy is here. So here, see, E must look like something like this. So let's see where E is. Okay, let's see E. E is equals to Y minus Y hat. Y is 1, 2, 3. Y hat is 1, 2, 0. Therefore, E is 0, 0, 3. Yes, 0, 0, 3 is equals to 3 times 0, 0, 1. And 0, 0, 1 is the basis. Oh, voila. So now we understand the language. E belongs to the W perp. All right, how to find W perp, guys? How to find W perp? Of course, in this very trivial example, you can visually inspect and see that the U3 is 0, 0, 1, right? But if you can't, so I'm going to give you a general idea. So the idea is this. It's back to your vector space question. Let U1, U2. So let us have a matrix U1 and U2. And in this example is 1, 0, 0, 0, 1, 0. And therefore, uh, uh, therefore, linear combinations of this is simply A times x1, x2, and therefore is x1 times 1, 0, 0 plus x2 times 0, 1, 0. Okay, so you see that A times x actually generates any place, any point in the space of W if U1 and U2 are the basis. So find W perp if columns of the space of A is equals to the vector space W. The column space of A is a vector space of W. See? U1 and U2 are sitting here. The columns of space of A means linear combinations of these two guys. Oh, that's what we said, right? W is spanned by these two guys. Same idea. So how to find W perp, guys? Any? Any idea? What are we trying to find? Who is W perp? So the first idea is W perp's vector must be what? Very good. Yes, it's a null space. And Dion says the null space of A transpose. Very good. So W perp is a vector that is what? Orthogonal to any linear combinations of A. So the null space of A is what? Ax equals to 0 is the set of x to make this happen. But what is A? A is 3 by 2. 3 by 2. What is x? 2 by 1. So x is a vector of 2 by 1. Not that we want, not something we want, right? We want the orthogonal vector against u1 and u2. And therefore, it must be the same size as u1 and 2. So now this is wrong. So this is wrong. Let's try another one. What about the null space of A transpose? What is A transpose? A transpose is U1, U2, right? This is A transpose. Times what? Times X. Who's X? And the null space means the set of this guy, set of this vector, such that this guy multiplied by this guy. Sorry. This guy, inner product with this guy is 0. This guy, inner product with this guy is 0. So actually, I should be writing 2 zeros here. So this guy dot inner product with this is 0. This guy, inner product is 0. Exactly what we want, right? We want the x such that it's orthogonal to this one. So the null space of A transpose give you W perp. Voila, equals to W perp. Okay, so once you understand this concept, then you're back to vector space again, and you can do the math. Okay, so I've spent 15 minutes now. Now I will take questions, guys. Please. Any? No? Really? Can you explain why you use the null space? The null space. Hmm. Okay. What is the null space again? Okay, let's try. You don't understand why null space give W perp. Okay. Mm, what for the... Okay. All right. Let's explain null spaces. A is equals to 1, 0, 0, 0, 1, 0. What is the null space of A? It is the set of X such that what? Complete this. Yes. AX equals to 0. So A is 3 by 2. X is 2 by 1. So the set of X is a set of 2 by 1 vectors such that A, this is X, huh? So the null space is a set with this condition. So it's a set of 2 by 1 vectors. So far, okay? All right. What about null space of A transpose? What's A transpose? 1, 0, 0, 0, 1, 0. This is A transpose. Let's call him B, okay? So that you're not confused. B, what is the null space of B? It is Bx equals to 0. What is B again? 2 by 3. What is X now? 3 by 1. So the X are orthogonal to who, guys? The X are orthogonal to what of B? What of B? Are orthogonal to the what? The rows of B. Ignore this guy first. B is equals to this guy and this guy. B times X equals to 0. Means that this row times this column of B equals to 0. So the rows of B are orthogonal to the X's. The null space are the rows. Sorry, the null space of B is the X such that the X are orthogonal to the rows of B. So what is A transpose? A transpose, A was this guy. A transpose make this column the rows because we actually want to find, what? We want to find another vector that is orthogonal to all these guys. So we just simply use the null space of A transpose. That's it. So I think some of y'all are confused because the transpose makes you, it is a double negative king. Not, how to explain a double negative? I don't know. Anybody can help me? Yeah, explain it okay? Can someone tell me? Or you are still confused? Please? All right. Okay. Is explain theorem 3 from 6.2.1. Theorem 3. Okay, let me try to find theorem 3. Oops. Oops. 6.3.1. This one? Ah, okay. Right. Okay, I'm going to get there, guys. Right. No, no. Okay, Jiahui, it's not perp, it's transpose. Yeah, why is W perp the null space of A perp? Because here is U1, right? Here is U2. So the column space of A is what? W. Can? Okay. 6.3.1. What is 6.3.1? 6.3.1. Okay, yeah, I'll get there. Okay. So we are almost 1 hour. Okay. Rest in peace. All right. Okay. 6.2.1. Okay, let me try. Oops. 6.2.1. 6.2.1. 6.2.1. Which one? 6.2.1. Theorem 3. Where's theorem 3? This one? Yeah. Theorem 3. Ah. Yeah. Okay. Uh, this one? Yeah. Okay. Yeah. This is why. Okay. All right. Let's try. So W. I say what is W? W is spanned by U1, U2. Agree? So I write it this. I say W is spanned by these two. Now I put U1 and U2 as columns in A. What is the column space of A? Column space of A is the what? All linear combinations, right? All linear combinations of the columns, right? All linear combination of column is exactly the same as span by. So actually now you'll see that span by and when we write A and in this form, they are the same idea. Okay. Then I want to find the null space of A transpose. The null space of A transpose means what? I transpose A first, and then I find the axis such that it is orthogonal to all these. So I'm finding the set of vectors that are orthogonal to all the columns of A and means W perp. Because W perp is spanned by vectors orthogonal to W. Okay? Is a basis spanned by. So you realize that we are just spinning around these two words. Huh? W is spanned by U1, U2. W perp is spanned by vectors orthogonal to W. We choose the basis, therefore we only choose a linear independent set. But then this is abstract. Okay. Concretely, what do? We go from W and we put it into columns of A. Now we know column space of A is all linear combinations. Very nice. We want to find orthogonal to these columns. What do? We transpose it first. Pa, pa, and then we find the null space. What is the null space? It is the set of X that is orthogonal to the rows. But the rows are actually the columns of A. That is why this our friend here says ne, the column space of A equals the null space of A transpose. Clear? Right. So where am I going now? I am going now to here. Oh, not here. QQ transpose. Let's now find QQ transpose. Yeah, I'm going to write this equation now for you guys. UU transpose or QQ transpose. Okay. Can someone tell me uh if 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 you guys are doing okay? Everybody? Okay. All right. Okay. Mhm. Okay. I'm going to do this. Y hat is the projection of y onto W, and then we span by octonormal basis U1, U2 to UN. And then, of course, we write y dot. Come, guys, follow me. What's the next word? No, W is a vector space, guys. W is a vector space spans by U1, U2, U3. I'm going to write this. And then, do I need to write divided by U1, U2? U1 dot U1? Do you think I need to write? It is octonormal because this guy, because this is octonormal equals to 1. So I don't need to write. So this, and then what do I write here? U1. Okay. So now I write simply U2, the scalar U2. Y dot UN, scalar UN. So everybody happy so far? Hmm. Any problem if I write it this way, guys? U1, Y dot U1. Any problem for the first element? U2, basically I'm just Y dot U2. No problem because this is a scalar multiplying by a vector. This is a vector multiplying by a scalar, right? Everybody happy? Yes? Any problem if I write this way? U1 dot Y. U2 U2 dot Y plus. Any problem, guys? From here to here, I'm just changing the order of the dot product. No, because A dot B is equals to B dot A, right? All right, now I write another way, U1 transpose Y. Any problem? U2, U2 transpose Y. No, again, because U1 dot Y is the same as this notation, U1 transpose Y. Okay? Now, any problem now? U1 and U1 dot U1 transpose Y is a what? Is a scalar. U2 U2 transpose Y. No problem, right? I'm just yeah. Now maybe the last one you have a problem. U1 U2 UN, and what will I write here, guys? I collapse, yeah, this to this. What do you think I'll write here? The first element is Y and Y transpose the same. No, 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 of course not. Y is the Y1, Y2, YN. Y transpose is the row vector y1, y2, yn. Okay? Can? U1 transpose Y and I don't understand. Oh, very good. Yeah, you guys got answer. U1 transpose Y. U2 transpose Y. UN transpose Y. So from this step to this step, any problem? No. Excellent. What's the left side again, huh? Okay, still Y hat. Mm, okay. What about the next step, guys? U1, U2, UN. So I did nothing but copy this guy. Now I'm going to expand this guy. U1 transpose, U2 transpose, UN transpose. This is, what's this, guys? Y. Yeah. So from here, I'm just expanding this, right? Each of these row, I take it out. So this guy is this number. The second row times this, transpose times this is the second number. Okay, what's this, guys? This is U, right? This is U. This guy? U transpose. This guy's Y. So Y hat. Wow, voila. So from the complicated equation we had originally, which was U1, U1 transpose Y plus U2, U2 transpose Y plus UN, UN transpose Y. These are the same. This is the vector notation. This is the matrix notation of Y hat. Okay, very nice, huh? Oops. So let's see. Why is U1 dot Y the same as U1 transpose Y? Okay. Hmm. Do you still need me to explain that, Jiahui? Okay. So okay, let's clarify. Mm, right. U let's let's revise. A dot B is what? The dot product of A and B. Yes? Okay, Jiahui? Is defined as the norm of A, norm of B, cosine theta. So the dot product tells us angle between the vectors A and B. But so this is the definition. It can be calculated like, so if you have the norm, okay, and you have the angle, you can find A dot B. It can be calculated like summation. No, let's forget about summation first. Oops. So let's assume that A belongs to Rn. B also belongs to Rn. Then it's A1 B1 plus A2 B2 plus AN BN. Then this equation, of course, is the same as summation AI BI equals to 1 to N. This equation is the same as A transpose B. It's the same as B transpose A. So this is the dot product in the many ways I can write the dot product. So therefore, when I write A dot B, I can also, or U1 transpose Y, this is the same as U1 dot Y. Clear? Shall we? All right. So I think I'm almost done. I can now go to QR decomposition. So the fourth topic is QR decomposition. So A is equals to QR. Let us have a 3 by 2 matrix. Oh, Nielsen asks if they are octonormal. Nielsen, do you see want me to answer? UUT, no, 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 no. UUT is no, don't do UUT. UUT will become a matrix. UTU, I think. Okay, let's try. So guys, let's begin. A is a 3 by 2 matrix. What do you think? Let's have a simple matrix. 2 0 0 0 3 0. This is still a 3 by 2 matrix, right? What do you think? What would I want Q and R to be? What does orthogonal, what does Q and R means? And what does A equals to Q and R means? There's a name for it. I what? I matrix what? I am what? I'm doing what onto a matrix? Is it factorization? Decomposition? Yes. So I'm decomposing matrix A into the product of two matrices. And when I do this, then I want the matrix Q and R to have certain properties. And Q have what properties, guys? The Q matrix is what size first? But if A is 3 by 2, Q have what size, guys? Same as A. Very good. 3 by 2. And what is the property of Q? So the size is the same. But this is for economical decomposition. What else? What is the property of Q? The word Q is very related to something. Orthogonality. Yes. So it is orthogonal columns. And in fact, we don't like orthogonal. We prefer octonormal columns. Okay? So in fact, we prefer this. We don't like orthogonal. We like octonormal columns. So Q is octonormal. So so now we have uh, octonormal columns. So what other property of Q, guys? If this is A, what is another property of Q? The columns of Q must what? The columns space of Q must be what? Come on, guys, let's try. Equals to the column space of A. Very good. Because if Q is not in the same column space of A, no matter what we do with R, we cannot get A. Okay, so Q have these three properties. R, what does R have? What's the size of R, guys? R is a what? It's a what matrix? Square, rectangular, square. Very good. 2 by 2. So it's 3 by 2, 3 by 2, 2 by 2, 3 by 2. Very good. So at least R is square. What else? The second property of R? Upper triangle. Very good. Upper triangle. Upper triangle. How do I draw upper triangle? It looks like this. So 0 below and values on top. So it's upper triangle. Then the third property, is it, now it's square, right? Is it invertible? A, friend, Phillips, Kelvin Phillips, almost. But A is 3 by 2. So A is not invertible. So it is invertible if what? Invertible if, yes, very good. Invertible if A's column are independent. So now we know what is QR decomposition in a conceptual sense. So now that we know what is QR, uh, how to find Q for A? Yeah, what did we teach in linear algebra? How to find Q? What's the process that we? There are many. There are at least three methods. Yes, Gram-Schmidt approach is one of them. But there are others, and we, I mean, you are not going to do that. Okay, so in the Gram-Schmidt, A goes in, the Gram-Schmidt comes out with Q and R. All right. Now I'm going to show you the MATLAB. MATLAB can perform economical or full QR decomposition. Let us see the economical first. In the economical, if this is 3 by 2, then Q is equals to 3 by 2, R is 2 by 2. Full Q is, yes, guys, yes, and R is R 3 by 2. Okay, let's try because our A is really simple, right, guys? Our A is really simple. Our A is only 200,030. I can even write Q for you. I can even write R for you without doing anything. Now let's try. Let's write Q. Come. What do you think Q will be, guys? The first column of Q. The first column of Q is related to the first column of A. So this is A1, this is A2. This is Q1, this is Q2. The column space of Q1 is the same as the column space of, please? Yes. So the column space of Q1 is the same as the column space of A1, right? So what do I choose, guys? What values will I choose here? Yes, 100. Because 100, same, right? It is just a normal vector of this guy. So in fact, the Gram-Schmidt always pick the first column and dump it there and normalize it. That's the Gram-Schmidt approach. Now, can I put -1 here? Quiz question. Is -100 a valid selection of a basis to to be to approximate, not to approximate, to span the column space of A1? Yes or no? Yes, because -1 is just pointing to the opposite direction of this, but opposite direction is the same direction. Okay? So I can put +2, +1. And then how do I reconstruct the first column, guys, in here? What values must I put here? So if I've chosen 100, what value must I choose? 2, because 2 multiplied by this column is 200. So it's 2. What about these values here? I haven't chosen here. So, all right. Now, because the example is so trivial, what do you think the Q2 is? This is Q2. Q2, guys? By inspection, you will know. 0, 1, 0. Okay. How do I? So, guys, now I'm going to need two values. Because, okay, oh, do I need any values here? I haven't chosen yet, but do I need any values here? Do I need any values here? This box A. To construct the second column, do I need the first column? Fortunately, no, because the second column is orthogonal to the first column, therefore the value is 0. This is 3. This is 0. This is R. And this is a very simple example because the second column has nothing to do with the first column. All right, let's see MATLAB. A equals to 200300. QR equals to QR A economy. And then we see, yes, exactly what we have written. Okay, let's see. Now I'm going to change some values. Ooh, okay. Right. So I think you got this right. Now, what do you think will happen? What do you think will happen if I'm going to now change? I'm going to now change QR equals to QR A foo. Or in fact, I don't even write foo, right? Let's see. Let's get our A back first. And if we do not parameterize the QR, can you see? Can you see that Q is now not 3 by 2, but 3 by 3? And that the last column of Q, yeah, is not needed to approximate A. How do I see that, guys? Okay, I'm asking the question now. So I will just copy A equals to 200030, and Q now is equals to 100010001, and R is equals to 200030. So the question is Q1, Q2, Q3. What is Q3 sitting there doing? Whose space does it span? Answer the quiz question. When do you need to use full and economical? You need to use, normally we just use economical if we want to reconstruct A. But if we want the full, what is Q3 representing? This guy is being used by who? This guy is what? Spanning what? Yes? Who is Q3 spanning? Spanning what? If Q1 and Q2 is spanning the column space of A, and if column space of A is W, what is Q3 doing? Yes, W perp. Yeah. Okay. And when do we want to use W perp? to know the error, right? Because the error will be projected into the W perp, if W is the space that we are projecting to. Y hat, Y hat is sitting on W. E is sitting on W perp. So, the W perp. Okay. Actually, I'm almost done. There's nothing much more I want to talk to you about. I think. Yeah, all right. Okay, then I'm going to ask you to do something for me. Can you just wait a while, please? Okay, just wait a while. Okay, I'm going to. Oops. Sorry, guys. Week 8 lecture. Okay. Sorry. I got. All right, guys. Can I ask you all to do this? Actually, I want to know how you all feel. Yeah, just use clap and is the code is WK8. And then just let me know how is it so far. And then I'll explain what Raja Mohan is asking. What is the usefulness of QR decomposition? Okay, can y'all try, please? Good. Okay, cool. Anybody? Yeah. Cook. Don't be, you all have to. The good news is that you all have so much resources now, and you have very excellent tutorials online and things like that. AV, yeah. So am I too slow? Maybe I want to know. Yeah, it could be better. Trust me. Yeah, I wish to. Ambiguous. Too slow. Ah. Okay, if it is too slow, I mean, I'm not taking YouTube. I'm not taking attendance. Uh, if you are not able to follow, I'm going to suggest that you watch other videos. So I'm going to show you which videos you can watch, and then they are they are at different speed. Okay, they are at many different speeds. Some are very fast, and some are very slow. So sometimes I do not know how to how to don't speed up. Okay. All right. Now, to understand what I've just said, actually, it would have been better if you have watched the videos, you understand about 80% or 70%, and then when you're actually listening to me, it will solidify. Right. Complex numbers TFT is the only part not covered in linear algebra textbook by Lei. Yeah, so in this course, you are guys are going to do complex numbers because used to be that complex numbers and statistics are one course, but they threw away the statistics, so complex numbers become our course. Complex numbers is also used in Lei. In Lei, the eigenvalue decomposition can result in complex numbers. So Lei assume that you know complex numbers. Okay, right. So I'm going to show you who can help you. Okay, so so I'll definitely read your comments and yeah. Now, if y'all are lost, so what y'all can do is this, okay, guys? Oops. Oh, okay. If what y'all can do is go to my website here, and then you go down to here, and you can pick any one of them you like, anyone, and they are all excellent teachers, and they are doing very similar things to us at different speed, of course. So he is the easiest to understand because he shows you everything graphically, but it's not enough to do our course. Okay, but he shows you the concept visually. This guys, of course, has more than enough to do our course. So if you can do the MIT one, this guy is also very good. He's a technion in Israel. This guy is King's College, I think, in London. Also very good. Okay, so you'll see that we teach it differently, and because I'm not going to repeat what I've just taught you in what I've recorded, right? So you see that I've recorded all these videos and I go through the slides. Here, I'm actually doing it in a different way. I'm doing it very much more similar to this guy, this old man Strength. He's just telling you, oh, I have a question, and now let's work on it slowly and slowly. Uh, so it depends. Okay. So if you do not need to watch this video, or your friends do not need to watch this video. Yeah, I mean, if you can understand all the lecture notes and stuff like that. Okay. So just learn however you like to learn, and as long as you can do the quiz and the lab and the quiz and the tutorials, you're fine. Okay, where are we? Yeah, I mean, I'm glad that you guys are telling me. What is POG? Pig? Three blue, one brown is pork? Pig? Could be better. Yeah, tell me about it. Now, if oh, awesome. Okay. Now, if I could be better, basically means that there's something wrong. I mean, I'm either too slow for you or I'm not good for you. So it's okay to go away. Yeah, I mean, do not need to do because you do not need to be here, right? Because I've already recorded the entire lectures as well as the tutorials. Okay, if I'm too slow. If I'm too fast, that means also if I'm too fast, I'm also a little bit worried. If I'm too fast, it also basically means that uh that you don't have enough knowledge to catch up. So you should try to watch those first. Okay. So if I'm too slow and I'm too fast, it's not a good thing. Overwhelmed, please advise. If you're overwhelmed, then the real idea is this: do all the tutorials and because I've already recorded all the answers, then you go and see all the tutorials are here, right? All the tutorials are here, 6, 7, 8, and yeah. So do them. Okay. So I think with that, I okay, if you're not able to follow also same means I'm either going too fast. So you have to watch the videos before you come here. So by today, you'll realize that I have finished, or I mean, I have I have done what I want to do for for the orthogonality. In the next week, I will go to least squares. Okay, so please go through the least squares and then do all this, and then in 1 week we'll finish least squares, 3 hours. All right, ambiguous. Yeah, I can't help you for ambiguous. You must tell me what's ambiguous. Too abstract. Mm, yeah, yeah, it's non-trivial. Okay. All right. So with that, please you can continue to update this, and I will try to help you as much as possible. Okay. Right. I'm not going to take any more of your time. I would get this recording and put it up and see. Hopefully, it is useful for you. But if you have already, if there's no need to watch this, really, you will realize that what I've gone through, I've gone through the same thing in the lecture video recordings in YouTube. Now, if you are watching it in YouTube, there's too much advertisement. Please put some ad blockers or download. Okay? Don't watch the advertisement. All right. Then that's it. It's weekend tomorrow, so enjoy. Thank you very much, guys. Goodbye.